All right, now it's time to relate equilibrium to a previous unit. So we're going to tie equilibrium into Gibbs free energy. So let's review what we know so far about delta G, Gibbs free energy. So delta G, either positive or negative. If it's negative, that means the reaction is spontaneous and will proceed as it is written. If it's a positive number, it's non-spontaneous and will not proceed as written, but rather will proceed in the reverse direction. And then delta G is also the maximum amount of work that can be done by a system. So that just means there's a certain amount of energy coming from outside the system, from the surroundings, if you heat it up or if you're cooling it down. But then there can be a certain amount of energy, free energy, that can be used by the system to drive its own reaction. So what we're going to look at now is the connection between KEQ and delta G. So when a system is at equilibrium, that means it is no longer able to do any more work. So it has no more energy to give, which means that delta G is going to be 0. So it's neither positive or negative. Does not mean the reaction is not happening. Okay, it's actually proceeding in both directions. The forward and reverse reaction are happening at the same rate, and therefore we get an overall change in delta G, or change in G, of 0. So here's a little chart to hopefully help us visualize what's going on between equilibrium and Gibbs free energy. So it's pretty complex. There's a lot of stuff going on here. Let's try and walk through it. So on our y-axis here, what we have is the delta G combined in both species. So our general reaction is just A at equilibrium with B. And so this would be the delta G for both A and B added together as we go up and down on this chart right here. And so if we have pure A, we have nothing but A in there, that's just our reactants. So our reactants is going to have a high Gibbs free energy because the Gibbs free energy is then what drives the reaction to proceed. And as time goes on, then we can see that A is going to decrease, which means the amount of available energy from A is also going to decrease. And then as it generates B, B would have its own Gibbs energy in the end. And so there's a certain amount of free energy available from B as well. And so then the change in G, remember that the change is the final minus initial, would be the Gibbs for B minus the Gibbs for A. So we would think that all the free energy from the pure A would be able to drive this reaction until it's nothing but pure B, so drive it to completion. But we can see that does not happen. Equilibrium lies here, partway through. And so what happens is the A is generated from its free energy, generated, until it gets to this point. And then at that point, it would have to increase its free energy in order to go to pure B. The universe will simply not allow this. So it's not going to be able to generate its own free energy to bring it up to that point right there. That would be a positive delta G, which means it would not be thermodynamically favored. It would not be spontaneous in that direction. So Gibbs free energy always moves towards 0 because it's negative and it happens until it gets to 0, but then it won't proceed past 0 because it can't become a positive number. That would make it non-thermodynamically favored. And so we think of a system that's at equilibrium, so it's right there at that point right there. What's going to happen then is if we're sitting there, okay, if it tries to proceed a little bit this one, back to A, okay, well, we see that that's a non-thermodynamically favored process, and so it's not going to happen. If it did get up there, then it'd be thermodynamically favored for it to move back down towards equilibrium. And same thing with the other direction. If it tried to produce more B, okay, we can see that's not a thermodynamically favored process because it's positive, but if it did happen, well, then it becomes thermodynamically favorable for it to move back down to that point right there. So as a result, the system will stay at that equilibrium because any budge from left to right is going to be pushed back by free energy. And this ties into Le Chatelier's principle when we talk about how it shifts, because if you add some A to the system, so if you increase the concentration of A, we say that it's going to shift to reduce that stress. And so if we add A into the system, that's going to be like moving our dot up here, and it becomes thermodynamically favored for it to proceed back down this way, which is going to produce more B, and so the reaction is going to shift to the right. Same thing if we were to add more B, so increase the concentration of that, it's going to shift to the left to produce more, or less of that. So for a reaction as written, if delta G is less than 0, so if it's a negative number, the process will favor the products at equilibrium, which means the KQ is going to be greater than 1 as well. So the reaction will proceed to equilibrium, and it'll do it in either direction. And we consider this reaction to be exergonic, which is just a fancy way of saying that delta G is less than 0. So all that we're really saying here is that a reaction that is thermodynamically favored, negative, is going to proceed towards products. We've talked about that already. That should already make sense. But how it ties into equilibrium then is it's not going to go all the way to products. So there's a point where that delta G is going to run out. The Gibbs free energy, the reaction is going to stop. And that's the point where it's going to hit equilibrium. And that's the spot where it's no longer thermodynamically favored for it to proceed any farther towards products. It's made all the products it needs to make. Products are favored. There's going to be more of them. But the reaction is going to be stopping a change in concentration. Now, if we look at the reaction of C to D, so another general reaction, we would do the calculation, we would find out that the delta G for this reaction is greater than 0, so it's a positive number. So then one would say, hey, this reaction is not thermodynamically favored, therefore it won't even happen. Well, it does happen. It's just favored towards the reactants at equilibrium. So we can see if we start with pure D, it's going to proceed really, really far until it gets to equilibrium. Whereas if you start with pure C, so pure reactants, it's not going to go very far before it reaches equilibrium. So even though this reaction is not thermodynamically favored, because it's got a positive number, it still will proceed up to a point until it reaches equilibrium. It's just not going to be very far that it goes, because it will be thermodynamically favored to reach that point right there, but it will go no farther. So when we talked about delta G before in the last unit, we said it was positive or negative, the value we'd be talking about would be the difference from here to there, right there. So that's the positive delta G. So overall, it is a positive number, but it will proceed ever so slightly in order to get to equilibrium. And we call this process an endergonic process. So that's one where delta G is greater than 0. So that means it favors reactants at equilibrium, which means that KEQ is going to be less than 1. Our number on the bottom is going to be larger. And the reaction will proceed to equilibrium in either direction. So if you have more products, it'll proceed towards the reactants. If you have reactants, it'll proceed slightly towards the products. So then in closing, delta G is equal to 0 at equilibrium. So that means even though the reaction is proceeding to the left and the right, there is no overall change in delta G because it's going to be proceeding at the exact same rate.